So we are given the story of a mass m which whirls around on a string, and the string passes through a ring at the center, and that the string is pulled with a constant velocity v, and that initially the mass is at a distance r0, and the corresponding angular velocity was omega naught. And we are asked to find the angular velocity as a function of time and the force needed to pull the string. So we know that the net external torque acting on the system is 0. The change in angular momentum must be 0. So by equating the initial angular momentum with the angular momentum at any time, we can solve this and find the function, but it is going to be a cakewalk. Let's solve this using polar coordinate system. So establishing the coordinate system, this is the origin point of reference, this is the r vector, and this is r cap unit vector along the radial line, and this is theta cap, the tangential or the transverse unit vector line. So acceleration in polar coordinate system can be derived to be along the radial and the tangential lines, and it is given by r double dot minus omega square r along r cap plus alpha r plus 2 omega r dot along the tangential or the transverse lines. So this is along radial lines, and this is along the tangential or the transverse lines, radial or the sliding lines. So now we know that as the net external torque is 0, the acceleration component along the tangential line has to be 0. So 0 is d omega by dt times r plus 2 omega dr by dt. Multiplying with dt, we get 0 is d omega r plus 2 omega dr. Now rearranging the function, we get 1 by omega d omega is minus 2 1 by r dr. Now integrating on both sides, w naught to w at a time by 1 by omega d omega is minus 2, integrating from r naught to r 1 by r dr. So this is natural log omega by omega naught is minus 2 natural log r by r naught. So exponentiating on both sides, we get omega by omega naught is r by r naught raised to minus 2. Omega by omega naught is r0 by r. So omega with respect to time can be written as omega naught times r naught square by r can be written as r naught minus vt the whole square. So this is the first equation they ask for. And now according to the image, tension in the string will act along this line, and that is acting along a direction that is opposite to the r cap unit vector direction. And we know that the acceleration component along the radial lines is r double dot minus omega square r. We know that taking it below, we know that minus tension is mass times the radial acceleration component r double dot minus omega square r. As the string is pulled with a constant velocity v, r double dot is 0. So minus t is minus m omega square r. So force needed to pull the string as a function of time can be written as m times omega naught square times r naught raised to 4 by r naught minus vt raised to 4 times r naught minus vt. So the final force equation with respect to time can be written as m omega naught square r naught raised to 4 by r naught minus vt cube. So this is the final equation. That's it.